Okay, hello and welcome to the second session of today. So my name is Alexander Fell, and I'd like to welcome you all to the second session. We have a nice lineup of speakers. And so how the session is going to work is the speakers are going to speak for like around about half an hour, 25 minutes. And by the end of the session, in around 2 hours, I'm going to send around links. So there will be breakout rooms. And so if you have specific questions to the speakers, just join the breakout room after the session is over. All right. So without further ado, let me introduce the first speaker. At 11 o'clock Central European time, it's turn for Borja Pérez. So Borja is a performance modeling engineer for the MEEP project in BSc, and his research interests include computer architecture, memory hierarchy, and heterogeneous systems. He received his Bachelor of Science and PhD degrees in computer science and engineering from the Universidad de Cantabria. So I hope I said this correctly. That is in Spain. And yeah, without further ado, please take it away.
Okay, thank you, Alexander. Let me try to share my screen now. Which I think I can't.
Alex, you have to unshare your screen, sir.
Okay. Like this.
Okay, thank you. Give me a sec. Can you see my screen now?
Yes.
Okay, thank you. So thank you again, Alexander.
You're seeing the speaker side of that versus the display if you want to change the
Okay, let me try again then. Is that better now?
Yes.
Okay, thank you. So thank you again, Alexander. I'm here today to talk about some early experiences that we are having when putting together Spike and Sparta, which are a simulator and a simulation framework, in order to be able to simulate architectures for HPC. And bear in mind that these are preliminary experiences, and you can think about this as our confinement project, because that's what we did during the COVID situation. And well, as you can see, by looking at the Roadrunner level, this is for the MEEP project. So let's start with a very quick overview of what MEEP is, just in case you missed the first talk of the first session. Okay. So the idea of MEEP is to dream the architectures that we are going to build in 2025. And to do that, we need a platform, and that's what MEEP develops. We are going to work on an FPGA-based platform to emulate architectures and to test and validate our ideas. And our thought is to make this platform both flexible and reusable, both within BSc and the whole EU. So we provide value to the whole community in the end. And to do that, we are going to take a look at the full stack. We are going to take a look at software, even including the OS, and then all the way down to the FPGA and to the hardware and the architecture itself. But before we do that, before we take a look at the whole stack, well, we have to think about the architecture itself. We have to think about what the accelerator that we are going to design and architect looks like. And as most of you might know, developing RTL is hard. It takes work, it takes time. So we need to be able to make some decisions before we start writing RTL on how the architecture looks. And to do that, we need simulation tools. Considering this, what are now the goals, not of MIP, but of the simulation tools themselves? And they are quite related, of course. The first one is that we are going for HPC architectures. And this is an overall goal, and it's the one that determines the rest of them. And of course, we are going for RISC-V, because I wouldn't be talking here otherwise. An important thing to bear in mind is that both scalar and vector instructions are very important to us and to BSc, because we would like to get that extra punch, both performance and efficiency-wise, by using vector instructions. And this is one of the requirements that conditioned the kind of simulation tools that we were able to use in our experiences developing this infrastructure. Then we also need a high simulation throughput, because we are going to go to RTL later. We don't need high fidelity now. We need just a tool that enables us to make high-level decisions and to test ideas before we go to RTL. So we need to compare at a high level. We don't need great detail, but we need to be able to carry out a lot of tests to decide what we are going to do next. And if those tests are slow, then we are lost. We are not going to get to the RTL ever. Then we also need these simulation tools to be flexible and easy to extend. And this is in line to the MIP goal itself. We need to be able to just test any idea that comes to our mind to make the best architecture and most efficient architecture possible. Apart from this, we would also like to be able to use existing tools, because there are already many simulators around for RISC-V, and we weren't comfortable just throwing a new simulation tool to the community, because there are already a lot of them there. And finally, and this one is the last, but maybe one of the most important goals, and it's related to the previous ones, our tool needs to be scalable, because we are in the HPC realm, and we are going to need to model quite complex systems. So we need to be able to get nice simulation throughput, regardless of the number of cores, catch levels, or whatever that we are going to model in the end. Considering this is what we would like to model. This is just an example, an abstraction, because if we were honest, we would like to model even bigger things. We would like to go as big as modeling 1,000 cores on a single chip, making everything coherent, but we know that that will be hard from a simulation perspective. So for now, this is an example with just 64 cores. We're ignoring coherence, and we consider this enough to get significant results and meaningful results to make decisions regarding the architecture that we are going to build in the future and then turn into RTL. So remember, HPC. So we need to be able to model a significant number of cores. As I said, we are targeting 64, maybe 128, and quite deep memory hierarchies. And as I said, we need to be flexible and to be able to extend the simulation framework. So because we are going to model very different things, I'm depicting here an L2, but that L2 might be partitioned in very different ways with very different degrees of sharing. Then there's a network chip there that might have different topologies, different routing algorithms. We might think about prefetching to move data around, the streaming, and who knows? We could think about anything, and we would like to be able to model that and to make decisions on the information that we get from the simulator. And as you might have noticed from what I'm saying, our focus is on the memory side of simulation. And this is because for our level of detail, we are not interested in smallest details of the course of the execution itself, but just in keeping those execution units fed, which gives us a picture of how systems are going to behave and lets us compare different configurations. And to do that, our idea is to leverage existing tools, because that adds value to the work that the community has already done. And before we started any development, we went through a journey across very different tools available already. And I'm going to go through some of them quite quickly. There are more that I'm not going to talk about, but the bottom line that we will get at the end will be the same. So first, we considered using QEMU for our simulations. And the upside of that is that it's very fast. You know about that. The problem is that after looking in the documentation for QEMU support for the vector extension, which is, as I said, is important to us, we saw that the support wasn't clear. So we didn't want to get into that way and then a few weeks or months ahead, notice that we can model what we want. Then there's Gen 5. And well, probably you already know about this. Gen 5 is a nice simulator. It's very detailed, but it's not the tool to go to if you want to model big systems fast. And also, if you've worked with it, you know that it's not the most straightaway tool to extend and to add stuff onto. But having said that, here in BSc, there's quite a lot of work that has been done on RISC-V for Gen 5. And in fact, Adrián and Osman are going to give you a talk later, so stay tuned. Then we also took a look at the tools by Renault, and they looked promising, but the problem was that they are focused on embedded systems, which is not our target, and they didn't support vector instructions, so we also discarded them. We also took a look at the Imperas tools. They also look nice. They support vector instructions, but part of them, their model is not open source. So we also discarded that because we wouldn't have been able to have control over the whole tool and modify everything to the extent that we wanted. Now we get to some more interesting stuff, which is the task simulator. This is internal to BSc, and it's interesting because the first part of the workflow runs on real hardware. Here, some folks at BSc have a RISC-V platform, a high-5 platform, which doesn't support vector instructions. So what they do is that they've got some software that traps on any vector instruction that is executed. And that trap goes to the host, and a trace is generated of the vector instructions that have trapped. And what they do next is that they feed that trace to the simulator, to TaskSim, and obtain some results into a paraver trace. And paraver is a tool that we've got here at BSc that lets us look at data and see what really happens in the applications. And all of this is really nice, but the problem is that the main problem is that it doesn't model the scalar instructions. Before, the problem was no vector instructions were modeled. Now the scalar are not there. And also being trace driven, the simulation throughput wasn't enough for what we needed in MIP. So we weren't able to use this either. Then there's a Spike. I'm sure you know about it, so I will not stay on Spike for long. You know, it's the golden standard for RISC-V. It can simulate multi-core systems. This is nice because we are going for a multi-core chip. Also has support for vector instructions, but there's no compiler support for them. So you need to hand program them using assembly code. And it's also a fast simulator. It runs at around 100 MIPS, and that's on my laptop. However, there are still disadvantages. It only models a very simple memory hierarchy, and it's poorly functional. So it doesn't know about timing. It just takes a RISC-V application, runs it. It does that very well, but that's all what it does. So we need something more. After that, we took a look at SST. And it's not a simulator, but a framework, which was developed by researchers at the Sandia laboratories. And this framework provides you with a lot of modules, more than 20, that model different parts of the hierarchy. You've got engines, which are the ones that drive the execution, and those are pattern-driven, trace-driven, execution-driven, whatever you want. Then you've got several cache configurations, several networks on chip. You've got different kinds of DRAM technologies, and you can build your system using that. This looked really promising because these are huge modeling capabilities and quite modular too. The problem, no RISC-V support, or very limited at least, because they only support one core, and this was really slow because it was basically a Spike plugged into it in not a very efficient way. You just generate a pattern using a Spike and then feed the pattern into the rest of the simulator, and it was slow. So not enough throughput, not for us. And then we got to Sparta. Sparta, if you don't know about it, is also a framework. It's not a simulator, but a framework to build tools. And it's currently developed by Sci5, just like Spike. However, the story of Sparta goes back 20 years or more into the past, because it was done by researchers and engineers that worked at Motorola, Samsung, and now they are at Sci5, and they took their knowledge and some of their tools now to Sci5. And this is industry-grade code that shows when you use it. And what you get with Sparta is basically a Lego box full of small pieces that let you build a simulator. It's not like SST, in which you get modules for a cache or a core or a network on chip. You are on a lower level and you get ports, you get abstract units, and you use that to build whatever you want. And this also has nice checkpointing tools, nice visualization tools. So it's a full set of tools that enable you to do simulation. However, what's the downside? There's no RISC-V support for Sparta, at least as of now. Considering this, the bottom line is that no current simulation infrastructure does what we need for MIP, which is a tool that is scalable and flexible. However, we noticed, well, Spike is the golden standard for RISC-V, and Sparta offers the tools that we need to build a model. So let's put them together. Looked nice, but however, it wasn't just as straight away as putting them together. There were issues. The first one is that what Sparta provides you is samples that are trace-driven and that are focused on the core. And as I said at the beginning of the presentation, we are focusing on the memory hierarchy for MIP to keep all the computing units fed. Then, as I said, Spike is purely functional. It doesn't know about timing. It just executes RISC-V. So there was some work to put them together. And after some thought and some experiments, what we decided was to go for this kind of integration, and we are going back to our abstract target system. And what we decided to do is to model the cores and the execution itself, and also the instruction and data L1 caches in Spike, and model higher levels of the memory hierarchy in Sparta. And the reason why we did this is to keep the interactions between Spike and Sparta at a minimum. So we get more simulation throughput while we don't lose much of the modeling capabilities that we need. And so basically what Sparta does is that it simulates instructions using Spike, and when an L1 miss happens, it handles it, it sends it to the model memory hierarchy, and it keeps track of time in the end, which is what a Spike can't do. And the overall functioning is quite straight away. Sparta is the one that handles of the simulation, starts running, and every cycle, it tries to simulate an instruction on each of the active cores. And why am I talking about active cores? Well, because when you simulate an instruction, it may result, or when you try to simulate an instruction at least, it might result in a row dependency. And if that's the case, the core needs to just stall and wait until that dependency is satisfied. If that doesn't happen, well, then the instruction is simulated using Spike normally, and Sparta checks for L1 misses, and if one has happened, then some events are generated, they go up the memory hierarchy, and everything that you wanted is modeled. And also, an event for the next cycle for the core is good. So straightforward, easy. But as I said, this requires some work, both on the Spike and the Sparta side. So I will start with the Spike side. Basically, what we did was to wrap a Spike into a class, and this class extends the unit in Sparta, which is the basic functioning element in Sparta. And then we created a small and quite neat interface between Spike and Sparta. And this interface has just 3 methods. One, to set up the Spike simulation, and it also sets up the L1 caches. To do this, we use the L1 capabilities that the Spike already offers. We had to do some small changes, but the bases are the ones that Spike offers. Then it tries to simulate 1 instruction per core. That's another of the functions that we offer, one of the methods of the interface. And there's a third method, which is to set a register as available for the row tracking. So straightforward. When you look at the code here in this table, I give you a very broad overview of the changes. We needed to set up a simulation, as I said, and that affected the simulation class. And also we needed to simulate instruction by instruction. That also had an impact on the simulation and the processor classes. And that's more or less 150 lines of code. Then you need to keep track of row dependencies. To do that, we modify the register file and the macros that are used to execute the instructions and to read and write registers. And that amounted to 50 lines, more or less. And last, you need to log L1 misses so Sparta can handle them. And that involves changes in the MMU and the catch classes, 60 lines. So the bottom line here is that we didn't have to go through a major rewrite of Sparta. It was just a few code placed in the right places, surgically located, but not a major rewrite. And as you can see, well, this is an ongoing project. We are working on making these changes even smaller by trying to avoid to modify the MMU and catch simulation classes. Now on the Sparta side, very good news. Nothing needed to be changed. Nothing needed to be changed. We just used the base Sparta classes. And as I said, we wrapped the Spike in a Sparta class, the unit, the basic functioning element in Sparta. Then we also encapsulated some other functionality in units. We modeled the L2. And to do this, we used an L1 that is provided as a sample with very minor changes. Then to handle the events, we used the Sparta event class to communicate elements such as the L2 and the cores. We used data in and out ports, which move the data and also generate events and add delays if you want, which are neat. And then to gather statistics, we used the appropriate classes to do that in Sparta, which are counters and statistic definitions. Now, let's see where we are and what we can currently model. Right now, we've got L1s, both data and instruction catches, and as I said, those go into Spike. And we can also model a banked L2, which is modeled in Sparta. It uses fixed latencies, which are configurable. So if you miss, it takes 1 time. If you hit, it takes another time lower. And we also have a couple of different data mapping policies for the L2s. And we can get some basic statistics, such as execution time, the amount of misses that have happened, miss rates, or the number of stalls due to the row dependencies. And we have performed some early tests using matrix multiplication, a regular DGEM, which has been compiled using the standard RISC-V compiler, which is the one that works with Spike. We've simulated up to 64 cores, which was our target, and we are getting between 5 and 7 MIPS of simulation throughput, which is enough to get significant results and significant information from the simulator. And again, this is running on my laptop, which is a 5th gen Intel i7 and 16 gigs of RAM. So when we can take that to a supercomputer, to Mare Nostrum, for example, we will get a boost. So I'm going to finish with some conclusions on our next steps. So first, we know that a scalable simulation infrastructure is necessary because we need to explore a broad design space to be able to compare different ideas and to design and to decide on the architectures of the future of 2025. However, there's no canonical simulation infrastructure that allows us to do this. And maybe this is somewhere that the RISC-V Foundation should focus, because as I said, this is necessary. However, with our work in the Sparta plus Spike integration, we think that we are getting somewhere, that we are on the right track to get a simulation that enables architects to do design space explorations. So our next steps, first, can we go faster? We think so. We are running at 5.7 MIPS. When you just run a Spike modeling DL1s, you run at 20. So there's some room for improvement there, not huge, but we are thinking about taking a look at the event engine in Sparta to make it more tuned to the needs of MIPO and of the kind of simulation that we are doing. And then we are on track to simulate more complex systems. So let's start doing that. And that's when the exciting part starts. So that's all on my side. I hope you've enjoyed this, and thank you. Time to ask questions.
Thank you, Borja, for this interesting and nice talk. We have a question from the floor, and that is with respect to Spec 2006 and 2000. So if you could quantify the accuracy a little bit, like what is like the error and so on.
Oh, it's too early to do that. And we are modeling a simple memory hierarchy, and this was the first step towards going to modeling more complex stuff. So what we are showing is that it can be done, and that we are in the ballpark of the simulation throughput that we want to get to. And then we will get to higher accuracy and start measuring how far we are from reality. But again, the idea is to be able to compare. So full accuracy is not necessary full accuracy is not necessary to get where we want to, which is to compare different design points.
All right. Then personally, I have another question. So do you know which kind of NOC you're using in this simulator?
What kind of, sorry?
NOC, you were talking about the NOC.
NOC, we don't have one yet. That was the picture that I showed is where we want to get, but as I said, we are not there yet. In fact, the NOC is probably what I will start working on next week, and I can advance you that we are going for a mesh. We are starting with a mesh, and we are thinking about implementing or modeling a 5-stage router and so on. So usual stuff, but right now it's not there. But probably if this talk were 2 weeks from now, I would have a slide talking about that mesh that would be there.
All right. Thanks a lot. Thanks a lot for this beautiful talk.
Thank you. I will answer so you can continue.
So the speaker will be available after the session is over in this lunch break. I'm going to send around the link so you can join then the breakout room during the lunch break and ask further questions there. So 1 second. Yeah. So our next talk is about designing open source RISC-V hardware with open source software. And we have 2 experts for this, Osman Unsal and Adrián Cristal. And let me shortly introduce both speakers. Dr. Cristal is co-manager of the computer architecture for parallel paradigms research group at BSc. His interests include high-performance microarchitecture, multi- and many-core chip multiprocessors, transactional memory, and programming models. He received a PhD from the Computer Architecture Department at the Polytechnic University of Catalonia. And he has a BS and an MS in computer science from the University of Buenos Aires. The other speaker is Dr. Unsal. He received the Bachelor of Science, Master of Science, and PhD degrees in electrical and computer engineering from Istanbul Technical University in Turkey, from the Brown University, and from the University of Massachusetts, respectively. Together with Dr. Cristal, he co-manages the Computer Architecture for Parallel Paradigms Research Group at BSc. And his current research interests include many-core computer architecture, reliability, low-power computing, programming models, and transactional memory. So without further ado, I would like to give control to the speakers. 1 second. There we go. Please take it away. Oh, I have to stop my sharing. 1 second, I do that.
Can I share my screen?
Mm-hmm. I just stopped the sharing. I cannot even do it.
Okay, so 1 second. Why I cannot get the... Okay, now.
So it just takes a minute.
Yeah.
Okay.
Can you see the screen?
Yeah, we do. Thanks.
Okay. 1 second. Oh. Okay. I go to present, the design open source RISC hardware with open source software. This work was done by our PhD student, Cristóbal Ramirez, and we are presenting it. Okay. What we go to do here is mostly to work on the vector processor unit. So we go to discuss first the architecture of the simulator VPU. And in this case, we are using like a base Gen 5. Borja was talking about the Spike+Sparta, and I think that there are two different approaches, and mostly the difference is maybe the detail at architectural level. So I think that with Gen 5, we go to have much better, we can say, insight about what happened with the architecture things, but also I think that the learning curve is much worse. And also maybe the timing in order to do the simulations. The second that we go to do is to present our first approach for a benchmark suite called RISC-V BA Live. We do previous work with another BA Live. So we differentiate the name in this way. Why we go to use the Gen 5 simulator? Okay, the outline, sorry. We go to first explain the Gen 5. After the background, what is a SIMD operation, multimedia extension, a vector architecture, what is the difference, at least some difference of them. What is our Gen 5 architecture-based model, and after the benchmark. Why Gen 5? First of all, we don't go to construct any chip if we don't do a simulation first. So we need a very detailed simulation in order to prove different alternatives and new ideas. And Gen 5, I will say that is maybe at least in the academia, I will say at this moment, one of the most useful or most used simulators. They have a different CPU model, interconnection topologies, memory subsystem, and there's a very large community behind it. Gen 5 can work in a system emulation or full system emulation, so you can do the both ways. And we also have multiple instruction set support: Alpha, ARM, Spark, MIP, Power, RISC-V, and x86. We have a timing model for the full cache hierarchy with support of custom coherence protocols. And we have multiple CPU models. We have an atomic, an in order, an out of order model. So this gives a lot of, we can say, flexibility in terms of different kind of things that we can do. Of course, has the complexity to program and modify is, I think that is much worse than in the Sparta models. Gen 5 has some vector support. We have Intel AVX, ARM-SVE. In ARM-SVE, I would say the Intel AVX is more like SIMD style, and the ARM-SVE is more a vector style. In our case, we go to provide an ARM-SVE, the maximum vector length is from 128 bits, so 2 words, up to 2048 bits, so 32 words of 64 bits. In the RISC-V extension, that is this word, we go to support larger vectors. So we go to start from the 128 bits, so 2 words, up to, at this moment, 256 words, but we can go bigger without too many issues in order to change this. But the idea, at least at BSc, is to develop a vector architecture for high performance processors. So we need, or the idea of the software people is that they can use very well, very long vectors. So we want to try and to experiment with this. So for this reason, we need a simulator with the large vectors. Backgrounds for now. We have, I will say, in vector architectures, 2 different things. Slightly the difference between them. Both of them are like SIMD, single instruction multiply data. In order to exploit data level parallelism, applying the same operation to multiple items of the data level parallelism. The multimedia extension, usually we have the SSC or AVX, that is for Intel processors, MCA for MIPS, Neon for ARM, and Altivec for IBM. And also what we call vector architecture or classical vector architectures that are, we can say, more similar to the Cray-1 vector processor are at this moment SVE, that is the ARM architecture. And at this moment, this is the first position in the top 500 supercomputed. That is the Fujitsu Fugaku. Also, we have the vector extension for NEC, in particular, the last model is Aurora, that also it has a very long vector, 256 elements, by the way. And what is this work? This is the RISC-V. The other that can do something similar, that is simply single instruction multiply data, is the GPU. Okay. Currently, the vector extension, we are in the version 0.9. We'll soon introduce the 1.0. The current specification includes a rich set of classical vector instructions as scatter, gather, reduction, iota, as well some instructions that are specific for RISC-V, widening, narrowing. It's a completely open specification. A specification focused more to support embedded system, IoT, and edge computing. I will say that it's not very good for HPC at this moment. I hope that it will change in the future. Initial implementation we have from Alibaba and the technology and are in this market segment. Okay, what is a SIMD extension, or what usually is a SIMD extension? We have here, 1 second, here, okay. This is our original code. So what we go to do is to check some SIMD or some chunks that we go to use in parallel. In this case, we go to do an addition of two vectors. So what we go to do this, and we go to do a 4. If you see the 4 is going for SIMD width, that in this case is 8. We assuming that it's cache aligned, so we start from the first address. We go to load the vectors in the BA, BC. We go to do the operation here, BA plus BD in the BC, and after we go to do the store of BC. And at the end, after we finish with the 80, that is, we can say a chunk of 8 values, we need to do the work in the tail. In a vector architecture, it's little difference. Usually in the SIMD operation, you do all the 8 operations in one cycle or one in 8 units. Here we divide the operation usually in lines. Can be from one line to the number of vector elements on the vector, the maximum vector length. And at least each line has usually, we can say, a slide of the vector register file and the unit. So it's something like you see in this image. In this case, what if we have only one line? Usually you go to the pipelining here. This will be this is what is the K1 model that was having only one line. After we go to start to add more lines. In this case, there are some differences. We don't need to have like two loops. We need to have only one loop because what we get with the set vector length is what has to be the maximum vector length that we can operate. So assuming that we have here, and we can do this, and we set the set vector length, maybe in this case it's 64, we go to get a chunk of 64 values. This chunk of 64 will be operated here, maybe in a pipeline way, because here we have only one vector lane. We go to the load, the same case, we go to the add, we go to the store, and after we go to increment the I, and after we go to do again accept the vector length with the rest of the total site that we want to.
May I just
we have only one.
We cannot hear you anymore. It's breaking up.
Sorry, I cannot hear you also. So I don't know what I can do. Osman, maybe you can try to continue because if I have bad connection, maybe you have a good connection. Sorry for that.
Okay, is this better? Can people hear me better?
That is perfect.
Okay.
Oh, I'm sorry, Osman.
I think you can change the slides maybe, then we can, or, okay.
Okay, I can do that. 1 second that I go to share again the, where is this one? I think that is this one, okay.
But now I can hear you well. I don't know, maybe it...
No, but I know that my connection is like crazy. It starts to be in this way all the time. Okay. I need to reset my router in order to be okay, because in 2 minutes it will be exactly the same.
Okay.
It's a router problem. Start to report.
So then I can continue. Maybe you can go to that slide.
Yes. 1 second, please.
Okay, so I think this is a, let's say, in the most basic, let's say, classic vector architecture type with the vector register file and the one lane. It's sort of like a classic, maybe style in the a la Cray. And when you look at the example, I think the difference between the SIMD version and this version is that we have here, we define the maximum vector length, and then we operate on the vector, unlike the SIMD case. So go to the next slide. Here you see another, let's say, implementation of a vector architecture with multiple lanes. So these would be operated in parallel. In this case, it's you see 4 lanes here. There's also the interconnection between the lanes, because you may want to do operations such as, for example, reductions that that can operate on that may necessitate communication between the various lanes. And this is the same example, but for the multiple lane implementation. So we can simulate both of these, let's say, different variants of the classical vector architectures. And on the right, you see how the code is structured here for the multiple lane operation. Next slide. Okay, so then I'll mention a little bit about the Gen 5 vector architecture based model that we are employing here. Next slide. So we are using this model also to do what if studies, and this is just maybe one example of so-called decoupled vector architecture model, where if you, Adrián, if you go to the the scalar core communicates with the vector unit, and the scalar core and the vector unit are decoupled from each other. The vector operations execute in the vector processing unit, whereas the scalar instructions run in the scalar core. So in a way, the scalar core is like a master, let's say, that sends the vector instructions into the vector architect VPU. And we develop this also to model the work that we have been doing in the European Processor Initiative, where the idea is to design a vector processing unit. And we can, in the simulator, it's parameterizable. So we can set different artifacts, different blocks. For example, we can change the number of physical registers in the renaming unit. We can change the number of entries in the issue queues, the type of issue, the reorder buffer, the register file, the number of read-write ports into the register file, the size, the maximum vector length, which is the maximum number of, let's say, number of elements that you can operate with. The number of lanes in the vector processing unit you can also change. You can change the latency of the functional units, define a different number of memory ports. We can connect to L1, or sometimes in vector architectures, you bypass the L1 and connect directly to L2 or main memory. And you can also change the lane interconnection topology. You can define it to be a ring or crossbar or any others. And also the caches can be set as well as the frequency. So it's quite flexible to model this, let's say, decoupled vector architectures, I would say. Next slide. So in the future, we plan to create part of the ecosystem for the RISC-V architectures at BSc. And mind you, this is just the vector processing unit part. And as Borja mentioned previously, so we have different levels of let's say, family of simulators. The Gen 5 is the more detailed one, but it's probably slower. And it also has a steep learning curve. Spike+Sparta is the learning curve is much faster, probably also faster. And we also have TaskSim or also Musa, as we call it, that allows a very fast operation, but with the let's say with comparatively less fidelity. And so depending on at which point we are in we would like to simulate, then it's possible to utilize one of these, let's say, different simulators. And we also want to, in the future, we want to model tightly coupled vector architectures as well. Okay, next slide. Thank you. So then in this section, we would like to talk about the RISC-V valid benchmark suite and preliminary evaluation. This is a vector applications benchmark suite. And by the way, this slide, you can see on the upper right corner, previous slide, this is our director, Matteo Valero, sitting on Cray supercomputer. We had been working with at BSc and before at UPC with Cray supercomputers, also the convex supercomputer on the left side. Both are vector processors. And so there's a long legacy of working with vector supercomputers, vector processors at BSc. And next slide, please. And in the beginning, the Valib, we had a previous vectorized library suite that was targeted more for the desktop and mobile applications, like the non-traditional, in this case, non-HPC-like vectorized applications. So we vectorized the applications that are part of mobile, let's say, mobile world. This is from 2014. So it includes speech recognition, speech synthesis, face recognition, computer vision, column stored database management system, and data mining. So this was sort of in the beginnings. And if you go to the next slide. And starting from that, then we would like to keep the name the same, the way lib, in the sense that it's a vectorized application benchmark suite, but for RISC-V. So we have the following 7 applications, and Black-Scholes, Canniel, heat diffusion, particle filter, pathfinder, stream cluster, and swaptations. If you look at the algorithmic model, they vary from dense linear algebra to structured grids, unstructured grids, dynamic programming, and MapReduce type. Next slide. And if you look at the characteristics, when we choose the applications, we wanted to exercise different aspects of HPC vector architecture. So, for example, for the vector length, we wanted to have applications that are short, medium, or large vector lengths. On the memory access, we want to have strided, but also indexed accesses. For the vector line, we don't want only arithmetic, straightforward applications, but also masked operations as well. So this is where you sort of operate only on the masked elements, and the others you do not operate in that instruction. And interconnection network, we want to feature applications which slide over a vector, the elements slide, or we also feature reductions so that we can exercise the interconnection network. And we also want to look at applications where, for the coupled vector architectures, feature intensive communication with the scalar core. Next slide. So very quickly, if we go for the applications, we have Black-Scholes to start with, and the parameters that we simulated for these were in order issue logic, 40 physical registers, maximum vector length from 512 bits up to 16K. Lane, we varied from 1 to 8, and the register file, we have 1 read-write port. So in the interest of time, I will go quicker here. For Black-Scholes, as you see, it scales very well because it's fully vectorizable, and most of the time it runs very well with the maximum vector length. So if you had a vector length of not only 16K, but 32K, 64K, it may be able to scale well with that too. Next slide. So the Canniel application is on minimizing the routing cost of a chip design, and it required a modification in the code to vectorize. And unlike the Black-Scholes, here the maximum vector length was 44, and you can see that in the speed up case. As we increase the number of lanes and the vector length, then we do not get as much as the Black-Scholes. So this type of applications are good to see what would be the ideal maximum vector length or how would you try to scale with this kind of this type of difficult applications, let's say to scale. Next slide is a typical Jacobi solver. So this is that models the diffusion of heat. This is also a highly vectorizable code. Next slide is particle filter. The specific feature for this application is that it uses mask-related operations like v-first or pop count type of instructions. Very useful, by the way. The pop count is a broad range of applications that this instruction could be utilized. Next slide. As Pathfinder is a sort of like a shortest path. It finds the shortest path on a 2D grid. Here we really stress the lane interconnection, so it could be a good application to test different lane interconnection topologies. Next slide. Stream cluster. This is a memory bound application, so it's good to test the memory system and how well, let's say, the design of the memory system is geared towards the vector processor architecture. Next slide. And Swaptions is also a financial application, and it uses a Monte Carlo simulation. The larger the vector length, it needs to use large blocks, and then it's kind of stresses the cache here in this case. So these are the 7 applications, and that concludes the vector RISC-V valid vector application benchmark suite. So we plan to have both the simulator and the benchmark suite open sourced. And thank you very much. If you have questions.
Thank you for this very interesting talk. We have a question from the floor, and that is, do you have a reference design for the out-of-order RISC-V engine? So this, it's asked if it's Adrián or anything else.
I think maybe since we are on the vector side, we have our, let's say, own baseline. I think Roger will talk about, let's say, the baseline case for where you have the scalar core, Adrián and others, and I think he will take that aspect later. I think after our talk.
All right. Then I would like to thank the speakers, and both speakers will be available after the session is over. So if you have further questions, just wait for the links to be sent around so you can join the breakout room. All right. So our next speaker is Frank. Frank is the director of Microelectronics Design Center that supports IC, FPGA, and PCB design within ETH Zurich. And he works as a senior scientist in a group of Luca Benini, supporting him in running the group. He has been part of the PULP project since its beginning, and he's going to talk about the 7 stories from 7 years of the PULP project. All right, without further ado, please take it away.
Hello, is the voice okay? I assume so. So welcome. I wanted to have a slightly lighter talk, not so much into the, let's say, nitty-gritty of the technical details. What they asked me to do is to highlight the open source aspects a little bit. So I'm going to tell you a story about how we started, how it evolved. And first I have to give you a brief summary of what happened. So the PULP project started in 2013 with the appointment of Professor Luca Benini to ETH Zurich. And we wanted to design energy efficient computing systems, and not only for one part, so we wanted to be equally energy efficient for IoT and HPC and all the ranges in between. The key points that we were looking at were parallel processing, near threshold computing, efficient switching between different operating modes, making best use of technology, and of course, heterogeneous acceleration. So out of these ideas, the project started. So we called it PULP, Parallel Ultra Low Power. It was a catchy name, we liked it, we kept it. So this is the boss, Luca, and he has groups both in ETH and University of Bologna, both larger and known universities. And me, I help him in Zurich, and Davide Rossi does the same for him at University of Bologna, but it's not us. The real work is being done by a number of PhD students and postdocs. And in total, we have about 60 people who work on projects related to PULP, both in Zurich and Bologna. It is a bit more in Zurich than it is in Bologna, so the pictures are not necessarily up to date. It's difficult to keep these completely up to date. And so the question that gets asked a lot is, why do we do open source hardware? And our main answer is because it's a necessity. We cannot afford to make everything ourselves. I mean, in these days, when we are making SoCs, we are talking about fairly large systems. Even student projects routinely have chips which have 6, 8, 10 processors in them. And if you want to be contributing, if you want to be doing something, you cannot afford to, redo everything by yourself. You need to have a way to collaborate with other people. It makes it very easy to work together with different groups quickly. And this is both a blessing and a curse. Your results are more trustworthy because it's not like I wrote a paper and I'm claiming something. Everybody can, or people who have the ability to do so, can download it and they can verify it. So you don't like my numbers about power, that when it gets mapped to a certain technology, download it, map it, and see it yourself. It also works. We weren't very sure about this at the beginning. I mean, we hoped it would work, but now I can say that we have actually more projects and even more funding due to our open source activities. And what is also very interesting for us is, we didn't plan for it. We ended up having very interesting collaborations with people that we didn't necessarily, were targeting or were thinking of. It just happened, and because open source allows you to get in touch with much more people. And also, it doesn't help that it helps others as well. There are many companies, universities, individuals that are using not everything, but maybe pieces of PULP, even commercially. And it's always interesting and cute to see that others are making use of things that you have done that you needed for yourself. So we use a permissive open source license. I'm going to talk about it, how this developed, and all our development is on GitHub. So the things that we can open source, that we are allowed to open source, are on the GitHub.com PULP platform. And the good news about the permissive license is it allows anyone to use, change, and make products without restrictions. Technically, you don't even have to tell us anything. You can just take it, make use of it. We have a large number of IPs. Most known are the RISC-V cores, or a lot of people talk about the RISC-V cores we have. I'm going to briefly talk about them, but it's not that. So you also need a lot of peripherals, interconnect, and sometimes accelerators. And what comes out of them are actually platforms that combine them. So we have the single core platforms, which we call Pulpino, and then the better one is the Pulpissimo, which is based around one processor core and memories, peripherals, accelerators, etc. Then we have multi-core platforms. Some names that you might have heard are OpenPOWER, Fulmine, and Mr. Wolf. And then we have the version where we have the same idea, so clustered cores working on shared memory that go over multiple clusters. So this was a hero. Andrea was talking in the morning a little bit about it, and in the afternoon, Jonathan is going to talk about OpenPython. That one, you can also read about that. And this spans actually a larger area of applications, all the way from IoT, where the single core microcontroller-like architectures are used all the way to HPC. So I want to talk about how open source hardware shaped our work. And I've chosen 7 chips that we had as part of PULP. It's 1 out of 37. And I tried to pick different times, different uses, and different technologies, also to keep it a bit more entertaining and different. So there is a story behind every chip, and I will concentrate mainly on the open source aspects. As Alex was saying, there is an open room afterwards, after the talk of Roger. You can come and ask questions. We can also talk about more technical aspects of the chip. So in addition to what we learned from their technical results, we also learned a lot about collaboration models, what works and what does not. So most of what I talk is available as open source, not all. There are reasons for that. Some of them we are not allowed to open source because there are some NDA restrictions on them. Some of them are not ready. In the morning, there was a question about ARA. So ARA is one such case. It's not open source, not because we are trying to keep it secret or we are trying to make money off it or something else. It just needs to make sure a little bit more. Mainly, it needs to the vector spec to stabilize a little bit. At the moment, it's a bit behind of what is being advertised. So let's start. Number 1. At that time, we weren't giving nice names, or I wasn't forcing people to use more names. So the chip was simply called PULP. It's our first chip, and it actually was in a fairly advanced technology at the time. In 2013, this was in ST Microelectronics 28 FDSOI technology. And we started with a bang, let's say. We had 4 cores on this chip, shared memory, second level memory. And at the time, when we first started, we weren't using RISC-V. We were using a modified version of OpenRISC. We called it Orion. And this was a collaboration with ST Microelectronics in France. They essentially needed a complete system demo, something more than ring oscillator, something that could show the possibilities of FDSOI. And this chip was clearly meant for a tester. You see on the right-hand side a picture of the package. There are a number of connections, about 60, 80 connections to the package, but most of them are for measuring power or for small individual parts. It has very few IOs. It was never meant that this chip would be something working on a board. And at this time also nothing was released. We were sure, we started the project from the beginning, we were 100% sure it would become open source, but we really did not have any idea how we could do it. And once you make a chip, you realize there's a lot of components that is tied to the technology, standard cell libraries, analog IPs, memories, and we quickly realized, hey, there's no way we can put this. We also learned, which was new for us, if you're working at a university, you cannot just on your own decide that you want to open source it. We worked for ETH Zurich, we had to ask for their permission, which also took some time. Then when you want to release something, you say, okay, what kind of licensing shall I use? We didn't know that, but we realized very quickly that we need the support of industry. This project was supported, meaning that the manufacturing was, for example, done for free by ST Microelectronics for this chip. And it is natural to understand that they wouldn't want to support some work if they were not allowed to use it, or if using our work meant gave additional restrictions to them. So if you're working with in this domain, technically, permissive licenses are the only way. Some purists will always condemn us, saying that it's not free enough, but for the things that we do, this is the only way we can work. This is what we learned at the very beginning things. Now in 2015, 2 years later, we have Fulmine. This one is in UMC 65. It's technically very similar to PULP v1. It has the same type of organization. It's a cluster with 4 OpenRISC cores, still not RISC-V. But this time, we are also adding accelerators to the mix. So we have one collaboration with TU Graz on cryptographic acceleration. And we have one on convolution engines, because guess what? Making fast convolutions seemed to be a good idea at the time. And this was meant as a chip for the boards. It wasn't meant to just be on a tester. We thought that we could put it on a board, and it has a number of interfaces. I'm going to come in a second. And it followed actually a number of such chips progressively so that we can reach this level. I'm very happy and a bit proud to say that IEEE Circuits and Systems awarded a paper that is cited here, the Darlington Award for Best Paper in 2020 for this thing. You can also see how long it takes actually for the work to reach an audience and then get appreciated. So this chip was actually, we taped it out in 2015. So this is much more than a core. This was a base to work on and expand. And let me try to get the laser pointer here. And in addition to the cluster that we have here, we have a number of peripherals, UART, I2C, I2S, SPI, etc. And we had the capability, so this is our shared memory infrastructure, and we had the capability of adding accelerators to it so that they have the same level of access like a core does. So the cores write to the same memory, the accelerators write to the same memory. There's an event unit that sort of kind of coordinates the things in between them. So it's our first chip with acceleration, and it's still not openly, I mean, at that point wasn't openly released, and we were using the third generation of the OpenRISC cores that we did. So right around this time, we were actually trying to figure out how to do an open source release. And you see that this is a fairly complex system, and we didn't want to do the first open source release with such a complex system. So we took the infrastructure, the peripherals, so the top part here, and merged it with a single core that has a separate data and instruction memory. Why did we do that? Because it was easy, it was fast, and that was February 2016. So this is Palpino, and there is some warning signs here. It's still the most popular release, name recognition-wise. Everybody talks about Palpino. We have much more advanced releases, but somehow this is better known. So here's your lesson. Your first release will end up carrying a lot of weight, so you have to be careful what you release first. We use SolderPad as a license. Our friends at Low Risk suggested this license. They had a lot of experience also going back to their involvement in Raspberry Pi. It's technically an Apache license with additional clarification, and we still use the same license. So from 2015-16, when we decided looking into it, nothing has changed. Now we move 2 years later, we have Mr. Wolf. This is from 2017, TSMC 40LP. It's now a much more advanced chip. It is a cluster with 8 RISC-V cores, FPU units, a number of RAM peripherals, and on-chip voltage regulators given to us by Dolphin Integration to be used as part of this chip. Now, this is a complete different result now. Mr. Wolf has been used in multiple systems, so we use it here in the drones. We have several development boards to test it. It was used in this system where we are sampling and processing biosignals. And we are still building boards with it even today. And the entire manufacturing consists of 200 individual ICs. It has widespread industrial use. For example, Dolphin use it to validate their IP in a more larger system. The GreenWaves GAP8 is based on the open source release of this project, out of which they developed, together with BitCraze, a deck that became the commercial version of this daughter board here. And in the meantime, GreenWaves has a much more advanced version. GAP9 is also a follow-up project. So this chip alone has done a lot of good. And you see what a difference 2 years makes. So at this point, when we release Mr. Wolf, most of what we have is already open source. It's a complex IoT processor. It's not the very, very simple Palpino with a simple core and divided instruction and memory. It has 9 cores, FPUs, shared accelerators, multiple power domain, power down modes. And we have now RISC-V cores with IMCF and then custom extensions that we try to accelerate different things. And it also allowed us to have a collaboration with Dolphin Integration, which is now part of Soitec. They have their IP demonstrated on a complex design. This is one thing, but they can also take whatever we made and share it with their customers without any limitations. So they do not have to ask us for permission, or we don't have to sign any agreements. The entire design is freely available, and they know that that design worked together with their IP, and they can give it to their customers to evaluate and work on it. And on our side, we get to use industrial IP in our chip on something that we do not have any research interests, but we have high quality IP that we can make use of it. So that chip has actually a single power supply for all the different power domains and things. Still, you realize many parts cannot be open source. We have a clock generator in there, which has analog parts. There are analog macros in it, IO cells, memory cuts, placement and routing scripts. We cannot always open source these things. And for example, the memory cuts, the choice of them, the organization of them have a lot of influence on the performance of the system. I think Roger will also talk about that in a while. Moving on to number 4, we have the lovely version VivoSoc 3.142. This is a much later chip from 2019, but there are actually a number of them. So this is the 4th or even the 5th one since 2015. It uses a fairly mature technology, SMIC 130/110, because there are many analog IPs which were developed here at ETH Zurich in a different group. But what you see here on the right-hand side is actually the similar PULP cluster with 4 cores, RISC-V cores, a number of memory that can provide the digital interfaces and also have post-processing for the analog signals that was collected. Now, the important thing is that PULP allows us to cooperate with basically everyone. So this is a collaboration between our group, Professor Benini and Professor Huang, another professor at the same department. But their work is not meant for open source. It's a more, let's say, traditional design. And you see at the top, there is a number of analog IPs that were being developed. They ended up in a succession of different VivoSoc versions. There was power management units, and then there was our developments going in parallel, and they all merged in this here. Here you can see actually the implementation. So this is the VivoSoc chip. Here you see the other side of the board. There is a Bluetooth IC and some connections. And here in the background, what you see is actually together packaged with the battery, the analog SoC, and then everything in a thing. And you also should realize the time it took to reach to this level of integration is several years. Now, when we talk about collaborations, this is one of my favorite things, Arnold. It's in GF22. It's a RISC-V microcontroller with an eFPGA. It's based around Pulpissimo. I'll talk about it in a second. And it started like this. I met the CEO and the representatives of QuickLogic by coincidence in a Global Foundries Technology Conference. And in 1 year of meeting coincidentally and talking about it, we had the chip taped out. And this is only possible of open source nature. If you're interested, the slides will be available. So this paper was put to archive at the end of last week, so it's brand new. You can also check out the details. The interesting thing is just because of this collaboration and different talks about it, QuickLogic has last week also made an announcement that they are going open source. They announced the QuickLogic Open Reconfigurable Computing Initiative, which you can see under that URL. So this is the platform that we were using. This is the, if you want, the more advanced platform for single microcontrollers. So here we have the RISC-V. So this is the RISC-V core. At the top, you have some memory banks. On the left, you have your IOs and a peripheral bus that is used to do the configurations. The eFPGA is connected to the system like an accelerator. It has fast connection directed to the same memory that the processor has. It can be configured over this peripheral interconnect. And it has multiple operation modes. It can directly act as an intelligent peripheral. It can act as a filter between input and memory, or it can work as a co-processing unit next to the processing core here. All it's an interesting way to collaborate. And I'm showing this because the next chip, number 6, Rosetta, is one of our latest chips, uses exactly the same model. It's in TSMC65. It is using exactly the same microcontroller structure, which is open source, but it contains independent blocks. As coincidence would have it, there are two groups in EPFL, the Embedded Systems Laboratory and the Communication Circuits Laboratory from EPFL. They developed some independently, some blocks that they wanted to test out. And we had two separate projects, and all four ended up being in this system. The individual projects are not necessarily related, but they all need to have some sort of processor, some sort of memory, some sort of thing to, you know, pass data back and forth and make measurements on them. So it works very well for us because we were already making a, let's say, fairly large chip. We have colleagues, they come and say, hey, we have an accelerator, how does it fit? And we see that it fits easily. And this is the way how we were able to tape out this particular chip. It's fairly new, so there are no publications at the moment of this chip. Just to explain the collaboration model, so there's a university, this is us, we commit into GitHub, into the repositories, people clone it. They may have some issues, may make some commits to these open source repositories, but they may also have their completely custom designs unrelated to anyone. Or we might be doing something together that ends up in GitHub as well. In this case, with EPFL, we did this, and what we have is the Rosetta. There is direct research collaborations or academic users we are aware of. This is a very difficult list and slide to keep up to date. If you are using it or are working on it, let us know. We'll just add it to the web page. The same thing also works with industrial users in maybe slightly different way. It goes the same way. So we open source it over GitHub. They use it. We have also projects where we develop custom IP for industrial users directly, or we have co-sponsored resources. And one such example is the things that we did with Global Foundries. And there's a series of chips. Andrea was talking about them in the morning. There are a number of industrial groups that we work with. Not all of them we make directly chips with, but there is a great interest in it. So the last chip I'm talking about is Baikonur from 2019. It has 2 Ariane cores. This was a project between Global Foundries and ETH. They wanted to validate their different libraries and flows for high performance or low power optimizations. Essentially, they have different ways of optimizing it for the technology, and they wanted a showcase which is not encumbered by IP licensing rights. It also has an automatic body biasing IP by Invecas, and it has various test modes to characterize everything. In addition to that, we were able to sneak in a little bit of additional payload. So there is 3 clusters of 8 snitch clusters in here and 1.25 megabyte shared memory for to be used for everything there. So Ariane is one of our most popular cores. This slide is from the keynote speech in ISSCC 2020. They're talking about their strategy of doing machine learning based automatic placement and routing. And the example they use is Ariane. So we have nothing to do with it. You see that they just ended up, because it's a larger block that they can freely use, ended up being there. We also have FPGA ports, and it is being used in many projects, EPI. We just learned that Hensel Cyber released a product or project out of it called MIG5. And in the afternoon, Jonathan is going to talk about OpenPython. So the last few minutes, I want to just say what happens to our course. So we graduate our course for a better future. Several of our open source cores are already maintained by different groups. So zero RISC-V became IBEX, and low risk is taking care of that. RISC-V became something like C3PO. And Ariane very recently became something C64 and is maintained by the Open Hardware Group. So this is actually an excellent opportunity for us. These groups have funds to support much needed but tedious work, documentation, verification, user support that we are admittedly not very good at. It also means that we have done a good job and creates opportunities for our graduates. At the moment, 3 of our members are in different ways and capacities involved with these 2 groups. Just to give you, highlight the fact that these groups are essential. So Zero RISC-V was open source since 2016, but the work on it really picked up when low risk took it over. So this is a graph they used in a conference last year. So in 1 year, you can see how much the contributions and the commits are increasing once they take it over. So without their support, the open source hardware IPs that you want to use will not become what they need to become. Open Hardware Group is another example of this thing. It's a not-for-profit global organization. It provides an infrastructure for hosting high-quality open hardware things. It has many partners. It's also a difficult slide to maintain because I have to go and make a screenshot every few weeks. At the moment, there are 30+ partners. They have many more resources than that, and they are doing work that we would not be able to do alone. And the list is alphabetic, but if you look closely, you might notice some smaller companies hiding in between them. And this is really important that the resources of these companies and the interests of these companies are in these things, because this will help everyone. So concluding, we benefit from our open source activities. For the science, it helps community building. It reduces getting up to speed overhead, so people can already start with things that work. And so that allows you to work on things that make a difference, and you can have fair benchmarking of whatever you do. For the business, it reduces the non-recurring engineering costs for silicon. There's a faster innovation path, new business models, and it helps exchange ideas across NDA borders before you are committing to a relationship with a company, for example. For the society, there is more innovation, growth, jobs, more secure, safe, auditable hardware, and bridges the gap between groups, as I said. Thanks a lot. I hope I didn't go over time, and I'm happy to answer questions either now or in the session in a couple of minutes from now.
Thanks, Frank. Thanks for this beautiful talk. We have a question from the floor, and that is, do you plan to use TileLink for Palpino SoC?
Well, let's put it this way. We are not going to make much with Palpino. Palpino, as I said, you know, I just try to explain to it. It was like, what's the simplest thing that we can do to learn how to open source things? We are still keeping it because if you're just interested in the core, Palpino is simple, it's very simple. So it just has the basic life support around the basic RISC-V core. And if your interest is in playing with the core, it's a good system. But other than that, if you want to make use of it, it's not very good. It's open source, so, you know, contribute to it. We will not be doing anything TileLink on it. Not that we are against TileLink, it's just that we don't have the time for it.
All right, thanks. So there are no further questions. The speaker, as he said, will be available after the session. So if you have further questions, just meet him in this breakout room, whose links I'm going to send around in a tiny little bit. Okay. So our next speaker is Borja Espasa. He is from SemiDynamics, and he's going to talk about hardening an academic core for industrial use. Mr. Espasa has lots of experience. Let me shortly introduce him. He got his PhD in computer science from the Universitat Politècnica in Catalonia in 1997. And between 1999 and 2001, he worked for the Alpha microprocessor group on the vector extension to the Alpha architecture. In 2002, the Alpha team was acquired by Intel, and therefore between 2002 and 2014, Borja worked at Intel developing a vector extension for the x86 ISA, which was initially deployed in the Larrabee and Knight's Corner product. And then it became the AVX 512 extension. Borja also led the team implementing the texture sampling unit for the original Larrabee chip. He worked on the core for the Knight's Landing product and led the core for the follow-on Knight's Hill 10 nanometer product. In 2014, Borja joined Broadcom, where he worked on a from-scratch ARM V8 wide out-of-order core supporting both A64 and A32. In 2016, Borja founded SemiDynamics Technology Services, And from 2016 to 2019, Roger was Esperanto Technologies' chief architect, where he developed a 7-nanometer architecture for machine learning. Additionally, from 2018 onwards, Roger is leading the design of the Sparo RISC-V core, targeted at high bandwidth applications and supporting an open vector interface to vector processing units. Roger has published over 40 peer-reviewed papers on vector architectures, graphics 3D architecture, binary translation and optimization, branch prediction, and media ISA extensions. He holds 9 patents with 41 international filings. Okay, without further ado, please take it away.
Thank you for the introduction. Is the audio okay? Let me share.
Yeah, we can hear you.
Okay, and now I hit share screen and the slideshow. Am I correctly sharing?
Yes.
Yes, okay. Thank you, and thank you, Frank, for going a little bit lighter. This talk will be even lighter than Frank's. So thank you for leading the way. There's not a lot of technical talk, but the organizer asked me to talk about, okay, you've taken open source GitHub cores and used it in industrial settings. What is it like? And I'm going to try to give you my anecdotal experience. No data, no statistics, just what I've seen happen and how it works. And if I click and I move to the next slide. Okay, so I'll start by saying the obvious. These academic cores are a great starting point. If you're a startup or even a big business, you probably want to start from one of those. It's not easy to choose. There's so many these days that actually you'll spend quite a bit of time just picking your favorite. But definitely my experience is that it's a great starting point, right? It's good for startups, it's good for big companies, it gets you fast prototyping. I think in the talks this morning, we've seen the many examples of how this happens and how you can make this successful, right? Then, you know, I've used Rocket from UC Berkeley. I've used Adrián from ETH, from which Frank was talking. And I was very happy with both. So, you know, let me, sorry, I think I skipped the slide somewhere. Yeah, so I'll do it this way. So let me give you a couple introductory words about what we're doing at SemiDynamics, so you get a feel for what I'm going to describe, where my experience comes from. SemiDynamics is a small startup, European based. Our previous project was a 7-nanometer machine learning accelerator where we used Rocket as our starting point, and we heavily modified Rocket to adapt it to what we wanted. And right now we're developing a RISC-V out-of-order core with a vector unit for the European Processor Initiative. And again, we started from Adrián, and we added to it the RISC-V vector extension. We're still working on it, heavily modified its load store unit, and you know, we're working on extensive re-verification of the core. So, you know, what I'm going to talk today is basically coming from these two experiences, like one 3-year long, the other one a couple years long. So it's like combined about 4 years of experience of hey, what happens when you take those? Sorry for the, you know, the screen flip here. So yes, there is a little bit of work before you can hit volume. And whatever I say in the next slide, still I think that you're much better off starting from one of these academic cores than you know, VI or Emacs, my first core .verilog, right? So I strongly recommend you use one of those. Source code, the first thing, one thing you'll have to decide when you pick one of these academic cores is, you know, for example, for Rocket, you have to decide where you're willing to work in Chisel, which is a derivative of the Scala language. The authors do claim big productivity gains. My experience has been that normal, and I mean by normal, it's general RTL designers that you can hire at industry are not happy to move to Chisel. That, you know, the Berkeley people will probably claim that's because those people are old-fashioned and they'll eventually disappear from the land of the earth. But it is a problem if you're starting a project this year and you need to hire people. Chisel might be a little bit of a problem. Adrián, in this respect, is much better. System Verilog better matches industry tools. Everyone understands that. You can just use it. Pretty much compiles everywhere. So that's obviously your choice. In general, my experience with both these cores is that they have very good coding styles. The code is very clean, easy to read, well organized. So, you know, kudos to the authors, both at ETH and Berkeley. And in the Chisel case, you know, obviously you need to understand Chisel, but it's still a well-organized code, and you can read it pretty nicely. Both have good assertions and coverage points present in the code, so that's good. You obviously want to add more, but they come with already good stuff in the RTL itself. I would probably say the only personal preference coming from other industrial projects is I really do not like flip-flops declared as always flip-flops. This may be a very minor thing or extremely religious, but I found a lot of benefit in previous projects to actually enclose the flip-flops in a macro, like the one reset enable flip-flop up there. You pick your syntax, uppercase, lowercase. Because that tends to force the state out of FSMs. I mean, certain people are better at making sure that the flip-flops are always at the end of the file. That's fine. But if you have a mixed set of designers, young ones, senior ones, it may be good for your team to enforce this little small religious choice, right? Obviously, you know, you don't have to follow this advice, but if I had to pick one coding thing to say I would change from these open source codes would be to make it very explicit where the flip-flops are located. That helps backend, helps front end, helps everybody work on that. Verifications, yes, one of the things you'll want to do if you want to go industrial and actually charge money after you take one of these cores and modify it is, you know, although they boot Linux and they're, you know, in very good shape, you'll want to invest in additional verification. In fact, we found small issues, not big, but we found small issues in this course as we were working on them and fixed them. And maybe we were not the best open source citizens because we have not fed back those fixes to the maintainers of the code. We should probably do it eventually if we ever find time to do it. So this is a list of things that you want to add additional coverage, you want to do more randoms. The user supervisor machine mode transitions are especially tricky, so you want to make sure those work and they work in the presence of debug, and that you can debug from reset and, you know, come out of reset and immediately catch a debug trap. Those are difficult things, and you'll want to make sure that you re-verify those and that they work in your environment. We also found some bugs in compressed instructions, a couple corner cases that are hard to hit. So, you know, those are things. So I have a slide, for example, on things we found, you know, on FP logic. You know, sorry, I have a sort of an animation here, but these are all very small corner cases. But obviously, if you go industrial, you want to have those things set, and mostly involve, you know, the floating point control status register was not properly set, right? On underflow, when result is denormal, the sticky bit was not set on the exact square root, causing a ULP difference. Again, rounding issues on fconvert for sign conversion. Underflow should only be set if result is also inexact. NV flag, 0/0 was setting the DZ flag incorrectly. You know, sticky bits, fconvert. I mean, this is a bit boring to enumerate this, but I hope it gives you a flavor of the kind of small mistakes that do not prevent Linux from booting. But if you want to take an academic core and really, you know, put it into high volume, you definitely want these things cleaned up. You know, about another 20 issues that we found on FP logic. So that's, you know, nothing too serious. It won't stop you from computing, won't stop you from running benchmarks and demonstrating your silicon, but you definitely want to fix those. The other area that, if you ask me, okay, when you take these cores, where do you work most? The answer would be the load store unit, right? very clearly the load store units in these projects, Rocket and Adrián, work. However, they're simple, right? So one thing, and Frank just got a question, hey, are you going to support dial link? Well, if you need coherency, your choices will change. Maybe the Black Parrot would be a better starting point if that's what you need, or Rocket if you like Chisel. If you like coherency, maybe Adrián is not your starting point. So that's something if you're from industry and you're choosing a starting point, you'll have to be cognizant about. Another thing I find usually the MIS pipeline is not the most optimized. And there are many opportunities there for improving. You know, some of these processors started their life as blocking caches. Then eventually over time, they went to non-blocking. Some started as non-blocking. So typically one of the first things to do is go non-blocking. State machines sometimes have many states programmed by someone that, you know, was just in a hurry and was not interested in optimizing the MIS case, but it's something very important to optimize. So, you know, you find this the state machine that will go like, oh, prepare to do a MIS, send the request, wait for the request, and maybe that's a 3-stage state machine that can actually be done in a single stage. And for higher performance scores, those things are important. You'll have to ask yourself whether you want to support hit under miss, hit under fill. How many misses do you want to support? Do you need a write back cache? So I do find in general that you will very likely heavily change the load store unit if you're going after performance. Another obvious statement is that you will repipeline the load store unit to match your exact SRAM array technology. You know, these cores work on many nodes and they have a given pipeline. And if you're optimizing for a given node, there are plenty of opportunities that you'll say, oh, wait, my SRAM is exactly 400 picoseconds. I could change my pipelining and match exactly, I don't know, give it 400 plus 100, 500 picoseconds and then re-pipeline the rest. So I think that's another area where if you're going industrial, you'll be spending time. Things like maybe, and especially in our case, we're doing a vector extension. We want to do 512-bit readout of the cache. So maybe what you got was an 8-way read that reads all the ways and flops all of them. That's a lot of bits if you're going for 512-bit readout. So that's another area where you may need changes. And obviously indirectly, and that's definitely not the fault of the authors, after you heavily change the load store unit, you need to make sure that, you know, watch points continue to work and that in debug mode, things continue to actually operate. So there's some work there to be done. And obviously change the PMA to match your SoC memory map. That's inevitable. You have your own SoC, you have your own memory map, you're going to be doing things differently, so you'll have to change the PMA for there. And another thing that you'll be doing, and this is a RISC-V problem, not an open source problem at all, is that there's no cache management specification, so you'll need to do that. Another area compared to industrial settings that usually is lacking is low-level clock gating. It is true that commercial tools are doing a really good job over the years at inferring clock gates, but you got to help them, right? You can't tell the tool, hey, insert clock gating for me, but in order to help them, you can have to expose the enable to a flip-flop very, very clearly. And that's where the magic of clock gating happens, where the designer goes and says, oh, wait, I can disable this flip-flop if there are no floating point instructions flowing down the pipe, or I can turn off these 8 big flip-flops in my tag compare array because, you know, there's no load operation coming down the pipe, so turn it off. That definitely is something you want to do, and that usually these academic cores don't have time to. Their students working on those, or the researchers don't really have time to work on these things. They're proving other, you know, big ticket items that take time away from this. So, you know, as you know, those of you that have done this job, you know, biggest bang ROI comes from very fine grained enables. So, you know, you'll you'll be doing that, and you'll be adding also what's called, you know, large module gating, like, hey, turn me off all the front end. I'm working on this vector instruction, so I can turn off the front end. This is also something you'll have to code in after you take this academic course. The SOC glue, if you take this academic course, you're probably putting that in an SOC. That's the most likely thing you're doing. And here, both Rocket and PULP, Pulpissimo, Pulpino. It was funny to hear Frank here how the first name is the one that stinks. Please, I strongly recommend you use all the goodies that are in there. You have pleaks, cleans, Aximaster slaves, debug modules, synchronizers, level shifters. There's plenty of really good stuff there, and you want to use it. It's been demonstrated in silicon, and you know, I would strongly recommend you just use from that. However, I'm sure you'll need something special, because otherwise you wouldn't be taping out something. So maybe you're adding lots of cores, or maybe you're adding lots of accelerators or something, and you'll still, even though you're going to use those goodies from those distributions, you'll need, you know, either special distribution of debug signals, a special network on chip, special intercore signaling. That's inevitable. So that's usually something that you'll have to do on your own, right? Another area that's important in industrial setting is errors. Okay, you know, an AXI device returns an error. What happens? Most of these academic projects will just ignore the error and move on with life, and you probably want to work there. And also you'll need fuses, and you'll need some form of secure boot, which again can be found in, I think low risk is providing some help there, but these is glue that you'll need as you move from, you take these projects and move into industrial, in the industrial world. So short to talk, I'm done. And I'll be happy to take questions and have debates if people want to. You know, first, you know, these academic courses are an excellent starting point. I've used them in 2 projects. Extremely happy of making that decision. They start booting Linux. They allow you to use an agile development methodology, like, okay, I have a working core, I change something, the test must continue to work. And this may seem very obvious to software people that are maybe listening. It's not obvious at all in the hardware world that people will follow these good methodologies, right? So starting with a working core, you can tell your designers that, hey, it's absolutely forbidden to commit a change if all the tests that we already have don't pass. And that's a really good thing to start with. They're well written, they're well supported, although in the previous talk, Frank said, no, they're not good at supporting it. Actually, they are. They're very well supported as a starting point. And obviously you'll have to add work. So we've gone over, you know, there are bugs in those cores that you need to flesh out. In my target market, in others, you may need to improve cache subsystem performance. And, you know, depending on your power targets, you may want to work hard on clock gating. That definitely is our case. And you will then compose these cores into something that's special for your product. So I'm sure that there will still be tons of work to be done beyond beyond just taking the core and gluing together. So my overall, you know, if you're a startup, if you're a research institution, if you're starting a project, I you know, strongly encourage you to start from one of these academic cores. And with that, if there are questions, I'll be happy to take questions.
Thank you for this beautiful talk. We have a question from the floor. And there's a group that developed a single cycle core with Chisel. And so they know the language of Chisel. But when reverse engineering the rocket core, difficulties are faced understanding the core, as there is no proper documentation of what is actually happening. So do you have any suggestion how to approach to study this rocket core?
No, I mean, my experience was that we started with Chisel. We trained 4 designers to write in Chisel. They did write some code in Chisel. And our experience is that the lack of support for something like, if you know Synopsys Verdi, their equivalent from Cadence and from Mentor, if you've worked on these tools, you know that when you're debugging in your waveform, you can double click, and you're going to find this a very petty answer, but you can double click on any variable in your Verilog, and it will take you to the waveform and take you to the source code. Lacking this kind of support on Chisel was what made us decide to go away from Chisel. So I'm afraid I'm not answering the question, and I do not have a good recommendation. I strongly prefer System Verilog over Chisel.
Thanks. Another question that we have is the RISC-V Foundation having a role to close those existing gaps and corner cases in the RV specifications?
The foundation has started working on the cache management operations specification. So eventually, hopefully, it's going to be with us. The RISC-V Foundation, I want to really separate. If I find a bug in an open source core, the RISC-V Foundation is not guilty. I should go back to the owners of that core and say, hey guys, on a fconvert, you forgot to set the inexact flag. That's the owner of the open source core that should fix it, not the RISC-V Foundation. But yes, those bugs that we found eventually will notify back to the owners.
So based on your experience, how do you compare the clarity of these open cores you mentioned to J2 core from Hitachi?
From Hitachi? No, the ones I know best are Rocket and Ariane. I think both are very clear. I prefer Ariane because it's System Verilog, but that comes from my preference of System Verilog. So that's not a statement about the quality of the cores. The Rocket is, more complete in the sense that it does support cache coherence. So if you need cache coherence, you may start from Rocket. I did not know Black Parrot that was presented this morning. I'll definitely look into it. Black Parrot looked very, very interesting from the presentation we had this morning at 9. That could be a very good option. That's System Verilog and cache coherent. So that's my answer.
Okay, thanks a lot. So the speaker will be available in the breakout rooms, and I sent around the links for the breakout rooms. Thank you for the talk.
Thank you for listening.
So this was the last talk of session number 2, and we are going into the lunch break a little bit early. So that gives us time to set up the breakout rooms in case they are not set up.